Next, let us discuss about the gravitational force and weight. The weight may be the most familiar force in our daily life. Okay. In physics, we define the weight as the gravitational force on an object. If we look at the object near the Earth's surface, we know that when an object is freely falling under the gravitational force, the gravitational acceleration is g. Okay, for a freely falling object. The gravitational acceleration is g. When we say freely falling, it means that there is no other force on the object, the gravitational force only. And from this, we have that the weight Fg, or sometimes we may use W as the weight, is equal to mg. And this is how we define the weight of an object. Okay. However, in general, there may be more than one forces act on the object, and the object under the gravitational force may not move. Anyway, we still define the weight from this equation, because we know the gravitational acceleration, and whatever or however the object move or not, the object move or not, we will define the weight of an object by the product mg. Okay. So it means that the weight is not always related to the motion of the object. If we look at this equation, you can see that the weight of an object linearly depends on the mass of the object. So it means that we can use the weight to measure. We can use the weight to measure the mass of the object. Once we know the gravitational acceleration, and if we can measure the weight, we will have the mass of the object. But by this means, the mass of the object is not directly related to the motion of the object. So this is different from what we defined before, the initial mass. And by this method, we say that we have the other definition of the mass, and we call this the gravitational mass. That is, we define in this way, we define the mass from the gravitational interaction, maybe between the Earth or the planet with the object. For the comparison, let us write down two definitions of the mass together here. Before we have the inertia mass, and this inertia mass show the resistance, of velocity change, but the gravitational mass gives us the strength of gravitational interaction. Anyway, we found experimentally that from experiment we found that the inertia mass is equal to the gravitational mass. So we can use these two mass interchangeably because they are equal. One interesting fact about the concept of the weight is that we can use the concept of the weight as the interaction between mass and the gravitational interaction. We believe that we can use this concept anywhere in the universe, not only on the Earth. We can use this concept on the Moon, on the Mars, or any planet, or anywhere in the universe. But it is obvious that for an object with the same mass, you will have the different weight in the different location. Even in the Earth, for the different altitude, you can have the different weight. And obviously, on the Earth and on the Moon, the weight of the same object will be different. So, we have to be careful about the weight, the concept of the weight of an object. Because you can have the weight anywhere in the universe, but it depends not only on the mass of the object, but on the gravitational acceleration also. So, when we say the weight of an object, we have to be careful because the weight is not an inherent property of an object. It is a measure of the gravitational force. If on the Earth, it is the gravitational force between the object and the Earth. If on the other planet, it is the measure of the gravitational force between the object and the planet. It means that the word weight is a property of the system. It's not the property of the object only, but for example, on the Earth, it's a property of the object and the Earth. So it means that you can have the object with different weight on the different planet, or you can have the object that have the same weight on the Earth and on the Moon, but the mass of those objects will be different, and the inertia property of those objects will be different, even though the mass are equal. This is interesting. If you look at this picture, the life support unit on the back of the astronaut is weight 300 pounds on the Earth and has the mass of 136 kilograms. And when the astronaut, when they are in training, they have to mark up the weight of the backpack to be 50 pounds with a mass of 23 kilograms, because when the astronaut work here on the Moon, the weight of the backpack is only 50 pounds. So it means that if he has to train, he has a training on the Earth, the backpack have to be 23 kilograms to have the weight of 50 pounds. So the astronaut will feel the same weight, but very different mass. So it means that, okay, he may feel the same weight, but when he moves, he will feel the different inertia of the backpack. So this has to be careful when they train the astronaut. It's a different feeling about the inertia, right? When they twisting suddenly or jumping suddenly, that is the effect of the inertia. It's not the mass. So you can have the same mass but different, the same weight but different mass, and it means that the property of the inertia of the object is different, even though they have the same weight. The second pitfall is that kilogram is not a unit of weight. This is a common language. Like when you go to the market, you can say that I want to buy the 2 kilograms of meat, but that is the measure of the weight. But actually, kilogram is not the unit of weight. It's the unit of mass, but when in the common language, this is the equivalent. And the most important is that it's valid only on the Earth's surface. If you buy the meat, the 2 kilogram meat on the Moon, it will have the same mass, but the weight will definitely different. So you have to be careful on this. And if you use the physics term, the kilogram is the unit of the mass, not the weight.